Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The general study of modules is a lot more complicated than the study of vector spaces, in part because the Hom functor is not exact. So what I want to do in this video is to study the Hom functor for modules and show that actually it's close to being exact. And in the process, we'll also see in what ways free modules are actually nice modules to work with. So basically, they behave well with respect to the Hom functor. More generally, I want to talk about projectives and injectives, and they're modules which also behave well with respect to the Hom functor. Okay, so let's get started. So let's look at this Hom functor and make sure we have it well defined. So our starting point, we have a ring. We'll look at the category of right modules over n. And we're going to have two functors. Okay, one is going to be Hom Rn blank, which goes from the category of right R modules to abelian groups, and Hom R blank n, which goes from right R modules to abelian groups. And this one is going to be contravariant. Okay, so how are these two defined? So let's just remember what it means to be a functor. So that means that you have to take objects in a category to objects in the codomain category, and also morphisms to morphisms. So let's see what's happening on objects first, and that's quite easy. If you're given an R module, okay, M, you can look at the R module homomorphisms from n to m, and that's going to be an abelian group, okay? So that's what happens on objects. What about on morphisms? Well, if you have a morphism in the category of R modules, that just means an R linear map, say f from m to m prime. So now let's apply Hom Rn to these two objects. So you get Hom Rn m and Hom Rn m prime. And if you want a covariant functor, so I claim this Hom Rn blank. So if I put an f in here, that's going to be give you a morphism in the category of abelian groups, so just an additive map from this Hom group to this Hom group. So I just have to define that for you, okay? So what is that? Okay, so if you're given a R linear map from n to m, okay, I want to get an R linear map from n to m prime, and there's a very simple way to do it. You take this phi, which goes from n to m, so now you're in here, and to get something in m prime, you just compose it with this f, okay? And once you do that, of course, since you're composing R linear maps, you get an R linear map, so you will get something inside here. And it's quite easy to see that, well, if you have a sum of two R linear maps here, this will get sent to the corresponding sum of maps over here. So this is a morphism of abelian groups. And you can also check that this is actually a functor. So you need to check that it preserves compositions and identity. So for example, if f is the identity map on the module m, so m equals m prime, then here, what does this map do? Well, you're just composing with the identity, which doesn't change this. So you get the identity on these Hom groups as well. Okay, so that's the Hom functor. And now what I want to do is to show you in this proposition definition how the Hom functor, even though it might not be exact in general, it's close to being exact. Okay, so in what sense is it close to being exact? Okay, so let's remind ourselves what it means for a functor to be exact. So basically, you start with a short exact sequence, okay, inside your domain category. So here it's the category of R modules, so 0 to m double prime to m prime goes to 0. So that means this map here is an injection, this is a surjection, and the kernel of this map here, this surjection here, is the image of this one here. So basically, in a sense, m prime is isomorphic to m modulo, well, the image of m double prime by the first isomorphism theorem. Okay? So functor is exact if it preserves short exact sequences. So when I apply the functor to a sequence like this, it stays exact, okay? And it will be an exact sequence inside the category of abelian groups if the functor goes to abelian groups. So let's apply the two functors that we have. Well, let's just concentrate firstly on this covariant one, apply it to it, okay? So we're going to apply it to, not the whole thing, but to most of it, okay? So apply Hom Rn blank to 0, you get 0. Hom Rn blank to m double prime, you get Hom Rn m double prime. And then this is a functor, so this gives you a map of abelian groups to Hom Rn and m, and also to Hom Rn m prime. And it will also map to the 0 here, okay? But what I claim is that if you apply the hom functor hom Rn blank, not to the whole of this short exact sequence, but everything except for this remaining 0 on the right, you'll get an exact sequence. Okay, so it's not quite what you would want with exactness. You'd also want exactness if you put a 0 at the end, but unfortunately that won't be true in general. It might be true some of the time, but not in general. So what's the bit of information that you've lost? So if it were also exact when you add in the 0, remember, that means that you also have exactness here, and exactness here, when you have a 0 over here, just means that this map is surjective. So in general, you don't know whether this map is surjective. In other words, if you have a homomorphism from n to this m prime, you don't know whether you can always lift it to a homomorphism n to m. Okay, that may happen, it may not happen, and it depends. Okay, so let's do the same thing with the contravariant functor. And remember now, being a contravariant functor, for example, if you have a map from m to m prime, you'll have a map going the other way on the hom group. So hom of r of m prime to n will go to hom r of m to n. And similarly, you can apply to 0, so 0 maps into here again. And then you'll have a map from hom r m into n into hom r m double prime into n. And again, we'll only apply it to this part of it, okay? And we won't do the last bit, which is the 0 here. And again, we'll find that always this will be exact. So the only obstruction to the hom functor being exact in this case here, okay, in the contravariant case, is again, you don't know whether this last map is surjective. So in other words, if you have, well, let's see what that would mean. So suppose you have an R-linear map from m double prime to n, m double prime to n. You don't know whether that lifts to a map from m to that n. Okay, can you extend that R-linear homomorphism to this bigger group? So this is essentially, this is an injection, so you can think of this as a submodule of this. Can you extend it from this m double prime to all of them? Well, that might not happen in general. But otherwise, it's an exact functor, okay? So the way we describe this, okay, being almost exact, but not quite, okay, in this case, is that the hom r n blank and hom r blank n are left exact. Because when you look at the short exact sequences that you get out, if you just look at the left-hand part, everything except for the trailing 0 on the right, okay, it's going to be exact. Okay, so, this is something that you know that's true in general. Well, let's suppose that for some n, this is always surjective. Okay, so in other words, the hom r n blank functor is exact. In that case, we'll say that n is projective. If instead the contravariant functor hom r blank n is always exact, okay, so you can always add a 0 here and get an exact sequence, then we'll say that this n is injective. Okay, so in some sense, they're modules which somehow behave well with respect to the hom functor. Okay, they're going to preserve short exact sequences, and so they're going to be useful. And hopefully, I'll show you a little bit later one of the many ways that you can use exactness of these hom functors to help you. Okay, so unfortunately, I guess this definition of projective and injective makes it look quite mysterious, and it's kind of hard to understand, you know, what does a projective module really mean? And I guess for the case of injective modules, it's actually quite tricky to understand what injective modules are. But fortunately for projective modules, that's not the case. So in this proposition, we'll see that a right R module P is projective if and only if P is a direct summand of a free module. So in particular, every free module is a projective module. Okay, so in other words, free modules, they behave well with respect to the hom functor. Okay, so hom of a free blank, okay, that's going to be an exact functor. Okay, and in fact, that gives you a pretty good description of all of them. Okay, that's pretty close to all of them, because the only other thing that you can do other than look at free modules to get a projective module is to take a direct summand of a free module. Okay, so that's rather nice characterization. Okay, so I want to say some words about why this is true to help you sort of like understand the meaning of projective. Okay, so what I'll do is I'll at least show this direction. Okay, I'll tell you why that bit is true. Okay, so let's look at a free module. Okay, and I guess to look at a free module, let's start with the simplest free module of all, which is R. I guess the first thing you should do is to show that R itself is a projective module. Okay, so we're looking at the hom functor, the covariant hom functor, hom R blank, and I claim that it's exact. That's the equivalent of saying that R is projective. And why is that true? Well, let's have a look and see what it does. Okay, so what is hom R of R into M? Well, I claim that it's just isomorphic to M. Okay, so it's naturally isomorphic to M, in fact. Okay, and if it's naturally isomorphic to M, okay, well, is that an exact functor? Well, that means that when you apply it to this short exact sequence here, basically it just leaves all these M double prime M and M prime fixed, so you just get back the same short exact sequence, essentially. Okay, so of course that's going to be a short exact sequence, and so this functor is exact. Now, if you haven't seen this isomorphism before, okay, and this is also a natural isomorphism as it turns out, I'll tell you how it works, and it's quite simple actually, okay? So I guess all I'll do is I'll tell you the inverse bijections, okay? So here, if you're given a R linear homomorphism from R to M, really it's just determined by where one gets sent, okay? So you just look to see where one gets sent. So you look, take this phi and you send it to phi of 1, okay? And if you know where one gets sent, essentially this is the universal property of free modules, okay, then you know what the homomorphism is going to be, okay? So in the other direction, an easy way to say it is that if you have a module element M inside here, okay, what is the map from R to M? Well, you just left multiply lambda M is left multiplication by M. You take a scalar in your ring and you left multiply by M. Okay, remember it's a right module, so the scalars R go on the right. Of course, since you can see easily that this is going to give you a right R module homomorphism R to M, okay, and this is going to establish this isomorphism. And you can check that it's natural too. So if you have morphisms in M, this isomorphism will respect that. So at least we've proved one module, the regular module R, okay, is a projective module. And then what about free modules? Well, free modules are just direct sums of copies of R, okay? And so to do that, I guess it's very natural to study the functor or hom functor when you look at a direct sum of things. Okay, so to complete the proof of this, I won't go through all the details, but this is the key point. If you have hom R of a direct sum n prime into M, then how do you get a homomorphism from here to here? Okay, basically you just have to say, oh, where does it send the elements of n? So hom R n M gives you have given an element of that, and where does it send the elements of n prime? Hom R n prime into M. So you just need a pair of such homomorphisms. And of course, every such pair will give you a homomorphism. So there's a natural isomorphism like that. So I have a direct sum here and I have a direct product here. I could have replaced this since there are two terms here with a direct sum. But if you want to have an infinite direct sum, I guess you should have an infinite direct product over here. Okay. So this will tell you that if you have a direct sum of copies of R, okay, then all you're doing is you just have a product of copies of hom R of R into M, okay, but they're naturally isomorphic to this M here. So basically, you'll just take copies of this. So this short exact sequence, you'll take direct sums of this several times or direct products of this several times to get a short exact sequence. And similarly, you can use this in the reverse direction to show that direct summand of a projective is also projective. Okay, so hopefully you believe me now when I say that this gives you a characterization of all the projective modules, which is really nice, okay? And it really explains, you know, in what sense is a free module a nice module to work with, okay? It's because when you look at this hom functor with this p in this variable here in the first variable, okay, it is an exact functor, okay? So remember, one of the points of homological algebra is you want to replace a module which may be complicated with a and try to construct it using more elementary modules. And the ones that we use were the free modules, and now I've kind of explained to you in what sense these free modules are nice. Okay, so to finish up this video, I want to tell you about a key lemma in homological algebra, okay, and to sort of show you how this exactness of this hom functor, for projectives can be used, and it's used similarly for injective modules as well. But we'll look at the projective case, okay? And remember that one of the themes that we want to emphasize in this playlist is that if you want to study modules, what you want to do is you want to replace them with a free resolution, okay? And more generally, actually, you can replace them with a projective resolution, okay? So you don't insist on free modules, but projectives are good enough. Of course, once you work with projective or free resolutions, okay, you work with more elementary modules, but you have a price that you pay, and is that you're looking at complexes, and one of the results of that is that you can only look at things up to homotopy as well. Okay, so bearing this in mind, let's have a look at this lemma. Okay, so what we're going to do is we're going to consider an R-linear map phi from M to N. And the question is that can you study this using complexes? Okay, so I'll give you the most general sort of lemma which allows you to do this. Okay, so in general, what you'll do is you'll look at a projective resolution of M and N. Okay, but we're going to look at a weaker situation. We're just going to look at two complexes which involve the M and N. Okay, the first one is going to be this one here. So you have this complex which goes to P1, P0, M goes to 0. And you're just going to insist that the P dot, okay, so remember, you can look at the left part of this and call this complex P dot. More technically, it's going to be a complex where you just replace the M with 0 and you just continue with zeros all along, okay? And this P dot projective just means that all these elements, P0, P1, P2, and so forth, they're all projective, okay? So this is a projective complex P dot. And it maps to this M, like that. So P dot maps to M. So this M here, you can think of as a complex with M in degree 0 and zeros everywhere else. Okay, so P dot maps to M. And then you're going to have a complex associated to this N. Okay, that's this one here. And what you want is this one is going to be exact. So normally if you work with a free resolution of this one and a free resolution of this one, then in that case, this will be, well, not only projective here, but also projective, and it's acyclic. Okay, here we're just assuming that it's projective, and then this being a free resolution, again, this will be projective and acyclic, but here we're just going to assume the other property, acyclic. Okay, so acyclic just means exact. So the key point is that then there's a chain map. You can lift this map phi from M to N to a chain map from P dot to N dot. And you can lift it in such a way, what does that lifting mean? It means that this square commutes. And the other thing is that, well, of course, well, how many ways can you lift it? Okay, you want to represent this kind of uniquely, if possible, or if not uniquely, you have to say, how many ways you can lift it, okay, and what are the differences between the ways that you can lift this map, phi dot from P dot to N dot. And the answer is that any two such are homotopic, okay? So I don't want to go through the whole proof of this, but the key point is that if you want to construct a map, okay, you need to, actually make up maps. And the way we're going to do this is we're going to use the projectivity property. And the projectivity property, remember, basically means that this map here is surjective. So given homomorphisms here, we know that we can always find here. So let me show you how this works, okay? And it's wonderful, and it's a classic sort of type of argument in homological algebra. Okay, so let's just write down this sort of diagram that we want to create here. Okay, so what I'll do is I'll just show you basically how you can find the existence of this chain map phi dot. Okay, so here we've written the first complex, and we've got the second complex, and the only thing we have at the moment is this map phi from here to here. And essentially for this to commute, it essentially means that we can make a morphismal complexes like this one here. I've added a little bit more information. So remember, what does exactness mean? Okay, exactness means that the kernel of this map here, so this is surjective, the kernel of this map, which I'll call this first syzygy omega 1, is also the image of this one. So the n1 surjects onto this omega 1. Okay, so we're going to use that in a little while. Okay, so what we want is we will need this chain map. So we need maps, vertical maps like this. So the first one is from here to here. Okay. And the point is that we can get a little bit close. We can't go from here to here, given what data we have here. We can go from this P0 to this N. That we can do, okay, just by composing these two. But remember, the Hom functor from P to anything is exact. So that means that the key point here is that you have surjectivity of this last one. That means that if you have a homomorphism onto an object, okay, then you can lift to anything which surjects onto it. Now this N0 surjects onto the N by this. So you can lift this map from here to here to here to here. That's phi 0. And since a lift, that just means that this square commutes now. Okay. And now, of course, you want to go down inductively. So let's just see how this works. Okay, so now the key thing is you want to create a map from here to here, and I hope you're getting the idea of what happens, okay? So essentially you want to say that you want to use the surjectivity here to create or find a map that you want, okay? The fact that this is surjective, though, and knowing that, it doesn't mean that you know which one to pick. It's a good one, but at least you know there's one that exists, okay? Of course, you want to make a map here such that this square commutes, okay? So, of course, let's start with this here, okay? So you study this one here. And I guess you'd like to do a similar thing, and you want to pull it up to a map to here. If this was surjective, you'd be fine. You could just apply, you know, the exactness of Hom P1 blank, okay? So that would be fine. But it's not necessarily surjective, okay? There's no reason why it will be surjective. Okay, in fact, usually it won't be. So let's analyze this a little bit more. So the first thing is that when you go to here, let's move it all the way down to here. And since this square commutes, that's the same as going around like this. But here you're composing two things in a complex, so you get 0. So going around this way is 0. So going around this way, snaking across like that, is going to be 0. So that means that you really land in the kernel of this map. So the kernel of this map is this omega 1. So really, this here commutes through this here. And the point is now we're going to use the fact that this is acyclic or exact. Okay, so the image of this is the kernel of that. So in other words, this is surjective. And since you have a surjective map now, this map from here to here actually lifts to here. So since this triangle commutes, okay, and this also commutes here, that means that this square is going to commute as well. Okay, and you can just keep playing this game, looking at further and further syzygies to construct a chain map. Okay, and then you can also ask, okay, what about the second part to show that they're homotopic? Well, basically you do a similar sort of thing. Okay, if you want to show that two such chain maps are homotopic, you just consider two of them, okay, and you look at the difference of them. And basically a homotopy is a set of maps which go diagonally backwards as well. So you need to construct maps from a projective to something. And the key point is that you can play this sort of game again, okay, using the fact that the Hom functor exact to keep finding homomorphisms that suit your needs, okay? So you can always say that there exists a homomorphism which makes a particular square commute. And that's the reason why you can prove this second fact that any two such chain maps, okay, lifting this phi, are homotopic, okay? So I like this lemma because not only is it very useful, but it really shows you some of the key ideas that's involved, okay, and how you can use the Hom functor and projectivity to prove results in homological algebra. I hope you enjoyed this adventure in pure mathematics.